Well, let's welcome next to the stage our next team. They're going to be talking about a study of nearest neighbor distances on a circle, multidimensional case. And to present that work, we've got Jeff Shen from Park Tudor School in Indianapolis, Indiana, Youkow Homma and Lyndon G., who are both from the Carmel High School in Carmel, Indiana. Welcome to the stage.
Good morning, everyone. My name is Youkow Homma.
I'm Lyndon G.
And I'm Jeffrey Shen.
And today we'll be presenting our project, Nearest Neighbor Distances on a Circle, Multidimensional Case. I'm going to begin by introducing our mathematical problem. Suppose we are given a one-dimensional region, a line segment of length 1, and an irrational number alpha, in this case, square root of 2. For each t, we scale the region by a factor of t. Then for each integer point that lies in the region at time t, we plot the product of that point and alpha onto the fundamental circle, which is shown in the lower left. The fundamental circle only considers the decimal or fractional part of a number, with the top notch representing 0. For instance, the bottom or halfway point around the circle could represent the points 0.5, 1.5, 2.5, and so on, because each of these numbers has a fractional part of 0.5. Now we take the difference between neighboring points on the circle and graph the proportions of the occurrence of the smallest, middle, and largest differences. On the graph, the left is the smallest difference and the right is the largest. As we increment t, we see that while the number of different points on the circle increases, the number of different distances around the circle never exceeds 3. Also notice that there seems to be a periodic trend in the graphs as the spacing with the greatest occurrence moves from left to right. We now move to an example from the two-dimensional case. We follow the same process, but instead of scaling a line segment by a factor of t, we scale a triangle, which is shown in the upper left. There seems to be a similar wave-like motion in the two-dimensional case. I will now give a more formal definition of our mathematical problem. We start the problem with a bounded convex region, R1, and a vector, omega, with components linearly independent over the rationals. Next, consider the integer vectors m and rt, where rt is the scaling of r1 by a factor of t about the origin. Then we order the fractional parts of the dot products, m dot omega, in increasing order. Finally, we take the differences between successive terms and call these differences spacings. In this project, we attempted to find multidimensional results analogous to those of the one-dimensional case. In particular, we studied the Steinhaus conjecture, which states that the number of spacings in the one-dimensional case never exceeds 3, and that the probability distributions behave periodically. We also looked at the results of Bleher, which state that the spacings have a rigid, discrete behavior. We also tried to describe the behavior of the spacings as t goes to infinity.
We now give the physical motivation behind our problem. The multidimensional quantum harmonic oscillator is given by the following Hamiltonian. We can see that the energy levels will be given by E equals E0 plus 2 times the sum of Lj omega j's, where omega j is determined by Kj, the spring constant in the jth direction. Moreover, these energy levels are the only ones physically observed. We are interested in finding the statistics of energy gaps in the high energy spectrum, as it is an important and unsolved problem with applications in the theory of highly excited atoms. In order to return to our mathematical formulation, we first normalize to make omega 0 equal to 1. After that, we are interested in the energy levels between a given E and E plus 1. Then, since typical transitions are from energy levels to neighboring energy levels, we are most interested in these nearest neighbor differences. We can see that this will reduce to the case where R1 is the triangular region given by the formula shown in t equals E plus 1. In the diagram below, we have an illustration of R1 in the d equals 2 case. For our project, we focused on a certain class of vectors. We say a vector omega is badly approximable if there exists a constant k such that for all non-zero integer vectors m, the distance from m dot omega to the nearest integer is greater than or equal to k over the norm of m to the dth power. In essence, this means that for m dot omega to approach an integer, the size of m must be relatively large. In this case, Boschernitz and Dyson showed that there is a bound independent of t on the number of distinct spacings. We found an explicit value for this bound by calculating the constant C1, C2, and C3 using a theorem of Castle's and by working through the details in this proof. In this case, we can show that there is a subcase called the algebraic case. We call alpha an algebraic number if alpha is the root of a polynomial p with rational coefficients. Moreover, if p has integer coefficients and leading coefficient 1, alpha is an algebraic integer. For example, cube root of 2 is an algebraic integer, but cube root of 2 over 2 is not. Using a theorem of Perron's, we can generate badly approximable vectors using appropriately chosen algebraic integers. For instance, if omega is 1 cube root of 2 cube root of 4, whose components form a basis for the cubic number field q adjoin cube root of 2, then omega is badly approximable with constant approximately 0.007. Before moving on, we first define a unit to be an element that is invertible in the ring of algebraic integers of our field phi. Then we can show that there is a finite set S in phi independent of t, such that for all t, every element of the spacings can be represented as a product of an element from S and a unit. We did this by classifying the spacings into a finite number of families, which consisted of a finite number of solution sets. Moreover, each solution set was generated by a representative element multiplied by any unit, which gave us our result. A special case of the algebraic case is a fundamental unit case. We call fundamental units such that every other unit can be written as the product of the powers of these fundamental units. A theorem of Dirichlet gives a way to find the number of fundamental units in a number field phi. We can see that the only case of interest is when phi is a cubic number field with one real embedding and two complex embeddings. Then we let u between 0 and 1 of phi be the fundamental unit such that all units are of the form plus or minus u to the n. In this case, we showed that there is a finite set S independent of t, such that if L of t is chosen to be negative of the ceiling of d log base u of t, then every spacing can be written as the product of an element from S and u to the L of t. We proved this by using the definition of L of t and also using methods similar to those in the proof of the finiteness theorem.
We now conjecture that the distribution of proportions for the spacings converges to a quasi-periodic behavior with respect to log t. More formally, we conjecture that there is a continuous function g mapping points on the torus to the corresponding vector proportions. At any t, the proportions are given by following a quasi-periodic flow on the torus and then applying the function g as illustrated in the diagram. We utilize what we call partitions of MT, where MT is a set of integer points in our region RT. The kth component of this partition is given by taking those vectors corresponding to the right endpoint of the kth distinct spacing, and thus they can be used to find the proportions of the spacings that are equal to the kth distinct spacing. Before moving on, we must first define n of y to be the three-dimensional vector expansion of an element in our cubic field phi with respect to the basis omega. We remove the first component of this vector to get a two-dimensional vector expansion m of y. We then proved a formula for the partitions that states that each component of the partition can be found by taking the intersection of MT and some translation of MT after subtracting out the previous components. We show a picture for t equals 100 and for the given region, triangular region, and for the given omega. Each pixel represents a point in the integer region MT. The color represents which spacing it corresponds to, and the color of the spacings are given on the right with a small spacing on top. Notice that for t equals 100 and for higher t's, that the partition can be seen as a series of overlapping triangular regions formed by translating the original region MT. Also, as t progresses, some of the components will grow as MT grows, but they may change color since the spacings are no longer indexed in the same way. Recall from before that each spacing can be given by a finite set S with j elements and the LTth power of u. Using this fact, we can replace all the vk's in the partition formula to obtain a new partition, pt, of the original region R1, which approximates the partitions of MT. We proved that the function f, taking the vectors of vk's to the corresponding partition, is in fact Lipschitz continuous. We note also that the vector of vk's can be described using a single variable, n of u to the L of t over t. Now, to get to a continuous function on the torus, we show in the pure cubic field case that there is in fact a function on the annulus taking points to the corresponding partitions. We first showed that n of u to the L of t over t is bounded by some constants, and also that the vector converges to a two-dimensional plane. Thus, there is a function with a small error term mapping points on the annulus to the partitions. The concept that the vectors n of u to the L of t over t are converging on an annulus are shown by the diagram on the left, and the diagram on the right shows how the projection of these vectors onto the annulus move inward as t increases. When the projection of the vector hits the inner boundary, the L of t will increment, and thus the vector will rotate and expand to the outer boundary. To get to the torus from the annulus, we must stretch and twist the inner ring of the annulus in three-dimensional space so that it aligns with the outer ring of the annulus, thus forming a torus. This would induce a continuous map from the torus to the partitions, and thus to the proportions, as illustrated by the following diagram. Since the writing of our paper, we addressed several issues with the conjecture. The first issue was that n of u to the L of t over t may not go completely from the outer boundary to the inner boundary of the annulus, and this is needed to get a continuous flow on the torus. We fixed this by redefining the way L of t increments in a different way. The second issue was that there are points of discontinuity on the inner and outer boundaries of the annulus, and we fixed this by reindexing the spacings using modular arithmetic. The last issue was that the partitions of R1 may not approximate the partitions of MT very well, but we suspect that the error term of this approximation is at most on the order of 1 over t.
In the context of related works, our work is significant because it improves on the result of Bose-Schneidson and Dyson by providing an explicit bound for the number of spacings. Furthermore, we were able to extend the discrete behavior of the spacings described by Bleher to the multidimensional case through our statements on the finite generating sets. Finally, through our quasi-periodicity conjecture, we improved on the Steinhaus conjecture by adapting periodicity to the multidimensional case. Our results are also more physically applicable because they are concerned with larger molecules. We also believe that because we use mathematical tools, our results may have possible pure mathematical applications. In the future, we plan to complete the proof of quasi-periodicity for the pure cubic field. We would then like to expand it to bigger fields. Also, the non-badly approximable case of this problem is largely unexplored. One very relevant question is whether there exists a uniform bound on the number of spacings if and only if the vector is badly approximable. By studying the quantum harmonic oscillator and the 50-year-old Steinhaus conjecture, we were able to provide relevant results in mathematics as well as gain a better understanding of molecular behavior.
We would like to thank our mentors, Dr. Bleher and Dr. Roeder of IUPUI, for helping and supporting us through this project, the Siemens Foundation College Board in George Washington for allowing us this wonderful opportunity, our parents and teachers for supporting us, the judges, and finally the audience for giving time and listening to our